I'll go ahead and start the recording now, and we can start doing these. Yeah, the whole point of 17 is just to demonstrate that you understand the nature of how electric fields work. In this case, they say draw a conductor, an oblong conductor in roughly the shape of a football. Which, that's close enough. Now, just draw a dozen or so field lines coming off of it. How would they go? Well, they come off in every place normal to the surface of the ball, or perpendicular. You'll notice I didn't count those. A dozen or so. There's enough going all the way around. You can demonstrate that you that's it. The main thing is to show that you know that the lines emanate perpendicular to the surface at every point. That's pretty much the whole point of that exercise. Say again? That's it. That was supposed to be a gimme point. I didn't mean to give you. Yeah, because it's a negative Q. The arrows need to point towards it. That's it. If it was plus Q, you'd draw the arrows pointing away. But it's not like you weren't having to try and solve a quantifiable problem. It helps when you do have quantifiable problems to solve. If you have that kind of an intuition, an intuitive grasp, an understanding of the nature of what it is you're working with, and when you do the calculations, they're more meaningful. Because remember, that's always one of the last steps you do is you look at your answer and ask, does that answer make sense? Now, you wanted number 16. An electron starting from rest acquires 4.8 keV of kinetic energy in moving from point A to point B. Okay. Point A, point B. Electron starts from rest here. And here it has how much?
48 or
4.8 keV. (4,800 eV) of kinetic energy. What are the questions? A, how much kinetic energy would a proton acquire if it started from rest at B and moved to point A? Okay. If you've got a proton, at zero velocity, there's zero kinetic energy. It's going to be accelerated in this direction. And acquire some kinetic energy. Okay, we know that because we know that this must be a positive point. No, I'm sorry, I got that backwards. This has to be a negative potential relative to the positive potential here, meaning that the electron is going to be repelled from the negative and attracted to the positive. Proton then would be repelled from the positive and attracted to the negative. So that's all that the direction is involved. It's all, and they cover that by saying if the proton starts here and is accelerated there, how much kinetic energy will it gain? Just without even looking at your calculator. How many, what's the net, how many electrons of charge does a proton have? No. One, it has the same charge as an electron. It has 1.6022 times 10 to the minus 19 coulombs of charge. Proton has positive charge, electron has a negative charge. If the electron travels through this potential and gains 4,800 eV, how much potential did it just pass through? 4,800 volts. So if an electron gets 4,800 eV going from here to here, how much will the proton acquire going the other direction? Exactly the same. A 4.8 keV. Actually, uppercase E makes that kinetic energy. So lowercase k makes it kilo, and lowercase eV makes it electron volts. Now, what's the next question?
The ratio of their speed.
That's
what's going to be different because their masses are different.
Exactly. They both gain the same kinetic energy, 4,800 eV. But they do not gain the same velocity. The same amount of energy for a more massive particle is going to be less velocity. So, what's the velocity of the electron? We've got 4,800 eV is equal to 1/2 mass of the electron times its velocity squared. We got to change eV into joules because this is in SI. Specifically, in this class, MKS. Go to a chemistry or biology class and you'll be working in CGS. Here we do MKS. This is not SI. So we've got to convert 4,800 eV into how many joules? 4,800 EV times how many joules per EV?
It's just 1.6022 times 10 to the 19 joule.
That's exactly right. Joules per EV. And that's what makes this thing, that's what makes it magical. That's what makes it work. 4,800 times 1.6022 times 10 to the minus 19. Everybody break out your calculators because you got some arithmeticing to do. Y'all are getting free homework points out of this. You can at least jockey the calculators. Cyrus, ¿qué pasa? Everybody make sure you've signed in. Anyone that didn't? Oh, it's right here.
I got a 7.70 times 10 to the negative 16.
Joules. Did everybody else get that? Okay. Now we can say 7.70 times 10 to the minus 16 joules is equal to 1/2. The mass of an electron is 9.11 times 10 to the minus 31 kilograms times velocity squared. Somebody look and make sure that I remembered the mass of the electron correctly. Okay. 2 times 7.70 times 10 to the minus 16 is? Okay, and then divide that by 9.11 times 10 to the minus 31. Negative what?
47. I did that wrong. Checking on that.
Yeah, everybody else do the calculation as well. Times 10 to the plus 15.
Oh, yeah, I plugged you in wrong.
V equals the square root of 2 times 7.70 times 10 to the negative 17 over the mass.
That's what I did.
Yeah.
We've got 7.7 times 10 to the minus 16 times 2 divided by 9.11 times 10 to the minus 31. And that brings us to 1.69 times 10 to the plus 15. And that's equal to V squared. That's meters squared per second squared. And if you take the square root, you end up with
4.09 times 10 to the 7.
yeah, 41
Yeah.
41 million meters per second. Okay. What's the mass of a proton?
1.6726.
Okay. The minus 27, 1.6726. So we've got the same amount of energy, 7.70 times 10 to the minus 16 joules is equal, in the case of a proton, to 1.67 some others times 10 to the minus 27 kilograms times the V squared. If we solve this one, we go 7.70 e to the minus 16 times 2 divided by 1.67 times 10 to the minus 27 gets us to 9.222 times 10 to the 11. And if you take the square root, we end up with 960 kilometers per second, or 960,000 meters per second. Say again?
Is that the negative 0.7?
Yeah, that's minus 27 for the mass of a proton. Because the proton is so much more massive than the electron, it doesn't get to going nearly as fast. In fact, if you ever get into particle accelerators, you're going to find out that electrons, they become relativistic before you can even blink. Up.
I did it wrong on mine. I didn't convert the 4800 EV to
joules. Yep, that'll definitely bugger up the works. What did I just erase? 96? There we go. Say again?
I said not squared.
Yeah, no, not quite. Now, does anyone else have a homework question?
So both of those.
Well, one's A and one's B, but yeah. 41,960,000. I'm sorry? Yeah, they want the ratio. That just means you divide them. What's the ratio of their velocities? So
you take the
41 million divided by 960,000. 42.7, but yeah, 42.8. To two significant digits, which is all we have. Or did they say 4.80 in the book? 4.8 or 4.80? 4.8. So we only have two significant digits. So to two significant digits, it's 42 is the ratio. Or rounded, 43 would it be? 42 point? Yeah. So it's 43 is the ratio. Everybody got all this before I start erasing? Nope. Ratios are always unitless. It's the
same thing.
right. That's why percentages are always unitless. Any more homework questions? All right. Did you sign in, Cyrus?
Yeah.
Was there someone else that snuck in, has not signed in?
I came in right as we started, but I got it signed.
Okay. Well then, let's go back to section 17.5 where we left off. We were talking about the potential or the voltage produced by a point charge. And we saw that when you work it out, you derive it from the E field. From a point charge of Q coulombs. That gives you the E field is the K times Q over R squared, the distance squared. Whereas the V, the potential, due to that same point charge, is just K times Q over R. You will also find it written as 1 over 4 pi epsilon sub naught times Q over R. But 1 over 4 pi epsilon sub naught is equal to K. So, example 17.4, the bottom of page 479, they ask, what is the potential due to either a positive or a negative charge? They say determine the potential at a point half a meter away, 500 millimeters away, from A, 20 microcoulomb charge, and B, a minus 20 microcoulomb charge. All right? Potential of a plus. And the plus would be, what's K? 9 times 10 to the 9? Am I remembering that correct? Times 20 times 10 to the minus 6 coulombs divided by 0.5 meters equals, somebody with a calculator, do the ciphering. What negative? No, that's 20 times 10 to the minus 6. So it's, say it again.
3.6 times.
So that would be 360,000 what? Volts. So if you can put 20 microcoulombs together in a point and get a half a meter away from it, that's how much voltage you'll have. All right. V minus is equal to 9 times 10 to the 9 times minus 20 times 10 to the minus 6 coulombs divided by 0.5 meters. There you go. Minus. That's it.
So when they're talking about determining the potential at a point, when they're talking about potential, they're talking about volts.
That's right.
Okay. That's considered your potential energy.
It's yes.
Okay, so kinetic energy, what unit is kinetic energy? Is that also in volts?
Kinetic energy would be how fast the particle is moving.
So it'd be meters per second squared. Okay.
Well, it'd be joules.
Joules, that's right. Okay.
So now, what if we have these 2-point charges? Half a meter here. So the distance between them is 1 meter. We just calculated the potential at the midpoint from both of them. What would the net potential be there? It's the sum of the two. So it would be 0. That would be your 0 potential point. Now, anyway, has everybody got all this before I start erasing? You know what? I got more board down there to use. I'll wait till I fill it up. If you look on the bottom in the column of 479, it gives you a graphical representation of how this 1 over R potential changes. As your distance gets smaller, as you get closer and closer to 0, your potential goes through the roof, just approaches infinity. It approaches infinity as you approach 0 distance. And then as R increases, it keeps getting smaller and smaller. And it does so quickly at first. The negative potential works just the opposite. And they both asymptotically approach 0. Where would you actually get to 0 potential, 0 volts relative? How far away would you have to get to reach 0 volts from that potential, from that point charge?
Would it be the midpoint?
You'd have to get to infinity. 1 over R approaches 0 as R approaches infinity. So, or stated differently, 1 over infinity equals 0. That's right.
We're talking about one single charge?
From a single point charge.
Okay.
Yeah, now you can get zero potential if you've got two and they're adding to, they can sum to zero. Okay, but
Not
you
in that
could,
case. If you have one single charge and then you try to get, you'll never, the potential will never get to zero.
that's right. You can never, you have to go infinitely far away from it. That's going to be a handy thing to know here in a few minutes. But now you could also put a Faraday cage somewhere, a conductive outer shell that, that the E field won't penetrate inside it, and there'll be a field-free, zero potential, zero E field inside that conductive sphere, if you will, conductive shell. All right. So yeah, you can have zero potential. You can have zero E field. But from a single point charge, its E field and its potential is going to reach all the way out to infinity. So, and we've already looked at how you add. They do an example here where they talk about the potential above two charges. Yeah, you know what? Before we do that, I want to do this. I do want to cover this. The work required to bring two charges together, two positive charges together. Suppose you've got a point charge plus Q right there. And you've got another point charge plus Q right here. How much work is it going to take you? Are you going to have to do? Because remember, you're moving it against the E field. You're pushing it to higher and higher and higher positive potential. And it is a positive charge. So you're having to do the work to get it closer and closer. How much work are you going to have to do to bring that point charge to, let's say, half a meter? We worked with that's what we were using a minute ago, half a meter. So let's say that is half a meter. And you want to bring this charge from way over there to this point right here. How much work will that take to bring it to that positive potential? Well, the work that you have to do, the work done by an external force, is equal to, or the work done, period, is equal to the negative of the change in potential. And we're going from A to B. Oh, of course. I was forgetting something. Times the charge. And if we're going from A to B, because what's the work? Work done against a conservative field is the negative of the change in potential. And we're going from A to B, where A, we will say, is infinity, and B is half a meter. So we're going to go from infinitely far away to that half a meter position. Well, now the negative of minus of VA minus VB, the negative of the change in potential is times Q. All right? And I need to designate these because they're different. So I've got the one that we're pushing, I've designated Q sub 1. The book calls it lowercase q. And the point charge that we're pushing it towards that's fixed in position, that's in a fixed position, I'm designating Q sub 2. So now we need to know what is the voltage, what is the potential at point B due to the point charge Q sub 2. It's K times Q sub 2 divided by 0.5 meters, the distance from it. That's our voltage at B, our potential at point B. Now we subtract from that the potential at point A, which is K times Q2 divided by, we're moving off to infinity, so when you divide by infinity, this goes to 0. And we multiply that by the charge that we're pushing, Q1. That means the total work done to get there is K Q2 Q1 divided by 0.5 meters. Everybody see how I got that? Can y'all see this over here? Now, in the example, they said Q1 is 3 microcoulombs and Q2 is 20 microcoulombs. So that becomes 9 times 10 to the 9 times, what is it, 3 times 10 to the minus 6 and 20. That's made that look like a Q. All divided by 0.5 meters. So I just wrote it microcoulombs, but you know that means times 10 to the minus 6 coulombs. So everybody do the math. How much work did you have to do? How much energy was required for you to push that, to put that charge? 1.08 joules. Apparently they said 0.500 meters in the book. Gave us 3 significant digits. Yeah. Now, let's do this one because we're going to, this one is important to, I want to work this next problem as an example. Find the potential above 2 charges. Because this is going to play directly into what we go to next, which is the potential due to an electric dipole. And there's something very important I want to make sure y'all see when we do that. So, calculate the electric potential at a point A due to the two charges shown, and then B at a point B. Okay. We draw us out. We got 50 and minus 50. Plus 50 times 10 to the minus 6 coulombs. Minus 50 times 10 to the minus 6 coulombs. Point A is directly above the 50 microcoulomb, the positive 50 microcoulombs, a distance of 0.3 meters. And point B, we're saying is 26 or 0.26 meters, which is the midpoint from here to here. And they're giving, they did the trig for you and said this is 0.6 meters and this is 0.4 meters. And of course, if there's 0.4 meters from here to here, then there's the same distance from there to there. Okay? So, what's the total potential at point A? It's going to be the potential from Q1, which is the positive charge, the plus 50 microcoulombs, plus the potential from the minus 50. Well, the potential for the plus 50 is simply K plus 50 times 10 to the minus 6 coulombs divided by 0.3 meters. And the potential due to the negative is going to be K times minus 50 times 10 to the minus 6 coulombs divided by 0.6 meters. And if we factor out our K, 9 times 10 to the 9, factor out 50 microcoulombs. Then that leaves us multiplying by plus 1 over 0.3 meters minus 1 over 0.6 meters. Somebody do the calculating. Oh man, I only got 20 minutes left. I'm not going to rush over this dipole moment thing. Say again? Is that what everybody else gets? Okay. Now, what do you want to guess is going to be the potential at point B here? Say again? It's going to be, we've got the positive one,
It's gonna be 0.4 both ways. So
We're going to end up with all of this times 1 over 0.4 minus 1 over 0.4, which is 0.
to the midpoint, you get 2 of the same charge, well, 2 of the same magnitude charge, different.
Yeah.
Positive and negative, 0.
They sum to 0. Now, our lab this week, tomorrow, is on capacitance, and I'd really hoped that we would get to the capacitance section. May end up having to do a little bit of explaining for the lab tomorrow, and then we'll just cover it on Friday in lecture. There isn't a whole lot left in this chapter once we cover capacitance. Of course, most of y'all are in electrical and electronics based fields, so it's not like we're going to skimp on the electrical aspects of this course. But right now, we're going to talk about a dipole moment. Dipoles are incredibly important in physics because, well, so many things are dipoles. What's the most powerful solvent you experience that you deal with on a daily basis? Water. Why is water such a powerful solvent? Because it is a molecular dipole. In fact, don't they have a picture of? Yeah, they give you the dipole moment of water here in this table on 482. But what's a water molecule? It's an oxygen molecule, which is net negative charge, bonded with 2 hydrogen atoms, both of which are net positively charged. What happens is those hydrogens, there's no net charge. The thing is actually neutral. But these 2 hydrogen atoms pull the electrons over to this side, or they push them, or I should say they push them away when they bond, because each hydrogen only wants 1 electron around it. So it ends up pushing extra electrons over to the other side of the oxygen atom. So you end up with a net negative potential on this side and a net positive potential on that side. You get a dipole, an electrical dipole. The dipole moment of water is 6.1 times 10 to the minus 30. And that makes it an incredibly powerful solvent. People don't think of it as being a solvent because it's generally neutral pH. It's not acidic or basic, left to itself. But if you drink pure deionized water, pure H2O with nothing in it, nothing but just pure deionized water, it can and will kill you. Because of that polar molecule, that polar nature of that water molecule, it wants to bond to something. I mean, what it'll do is it will create a tremendous osmotic pressure across the cellular membranes of all of your organs and tissues. And it will actually start rupturing cellular membranes. And if it doesn't kill you, it will make you sick. And it may kill you if you drink enough of it. This whole notion about wanting to drink pure water is mountain spring water is not pure water. Okay, at the molecular level, there's all kind of minerals and salts and other things that have been dissolved into that water. That's why things dissolve in water so well. Its pH is neutral. It's got a pH of 7. It's neither acidic nor basic, which means it won't burn you. But if it's pure water, it can and will kill you. At the very least, it'll make you sick.
So like alkali, like alkalis.
Alkalis are basic. They have a, and everybody ask Google before you quote me on this, because I never can keep it straight which one goes which way. But basic, I think a pH below 7 is basic, and a pH above 7 is acidic.
Yeah.
Or maybe it's the other way around. I don't know.
I use it that way.
Above 7 is alkaline and below 7 is acidic. Okay, that's however you get there. 7 is neutral. 7 is neither acidic nor basic. So, but it doesn't need to be acidic or basic to burn you, to hurt you if you drink it. So, let's talk about a dipole. We've got 2 point charges, minus Q and plus Q. Now, the question is, what is the potential from those 2 point charges at that point way up there? Well, you try to draw a straight line. Okay. I'm going to move my point, but go from there to there. So what is the potential at this point here from those 2 charges? Well, let's start by noting that these 2 charges are L apart. That's how far apart they are. That's the distance. And now we're going to call this distance from the positive charge to the potential point as R. That's our distance, R. Now that means the distance from here to here is also R, plus this extra little distance. Now that's a right triangle, which means L is the hypotenuse of this little right triangle. Can everybody see? Now I'm going to draw this triangle, but I'm going to rotate it around so you can see what we're looking at, and I'm going to make it bigger. This is L. Okay? You see what I've done? I've taken this triangle and I've rotated it and flipped it up here so we can see what I'm drawing. That is the angle theta right here. Yeah, and of course they did. They're going to say that this is theta, which is the angle of this moved away. Okay.
What's the other corner on the other picture?
Yeah, that's exactly. That means this is theta. Now, which is approximately equal to this angle here. Okay? Anyway, what we want to know is this distance here. which is the adjacent side of the right triangle. And it is going to be equal to L times the cosine of theta. We're going to call that little piece delta R. You see, we've got R, and then this extra little bit, delta R, as the length from this charge to the point. Okay. Does everybody see what we've got so far?
Now, if we wanted to find the opposite side, we'd use sine, right? Sine theta.
Yeah. This would be
Sine theta.
right. So, now, what is our potential up at that point? It is equal to K times plus Q over R plus K times minus Q over what? Nope. R plus delta R. Now, we can factor out our K and our Q and bring them over here and get them out of the way, and that leaves us with 1 over R minus 1 over R plus delta R. Everybody see how I've gotten there? All right, because now we're going to simplify this. And if I multiply this by R plus delta R over R plus delta R, R plus delta R over itself is equal to 1. I can multiply this like this and I don't change anything, right? And from that I'm going to subtract, I'm going to multiply this by R over R. Which doesn't change anything because R over R is 1. Now that means I've got R times R plus delta R and R times R plus delta R. That's my two common denominators. So this becomes R plus delta R minus R. See? This times 1 minus this times 1 is just R plus delta R minus R all over R times R plus delta R. Anybody? Everybody with me? Yeah. These cancel out. So the potential at that dipole, at that point from a dipole, is K times Q times delta R over R times R plus delta R. Now, in the case where delta R is much, much, much smaller than R, this is effectively R squared, Just R times R, R times R. Problem here is it is entirely too easy to wave my hands in the air and say, oh, this is small enough we can just ignore it. You need to know why we can ignore it. You need to understand this, that just because someone says it can be ignored doesn't mean it can be ignored. What makes it, why is it true that because if it's smaller than R, if it's much, much smaller than R, why will it be true that we can ignore it? Bingo, you're both exactly right. If we do the math, we get R squared plus R times delta R, where delta R is much, much, much smaller than R. Okay? That means R squared plus a very, very tiny percentage of R is in that denominator. If you've measured your best measurement out to 4 significant digits, and the addition of this little perturbation in the denominator only changes something in the 6th or 8th or 9th decimal place, how does it change your measurement? It doesn't. And so it isn't just that you can get away with ignoring it. It is truly the case that if you don't ignore it, if you work through all that extra math, it's not going to change your measured value one bit. It's not going to change your measurement. It's not going to affect the significant digits, then it doesn't matter. That is why you can, in this case, ignore the place, that delta R in the denominator, and we end up with over R squared. Now, you'll notice I did not throw away the delta R in the numerator. Because there, it doesn't matter how small that is, especially if it's a little tiny coefficient. It can drastically change your measured value. Yeah, it doesn't matter how big this is. The smaller this is, the more it's going to change this, because you're multiplying it by a smaller and smaller number. You're making it go smaller and smaller fast. It's not like you're multiplying it times R plus delta R, where the delta R doesn't change any. It's only changing the 9th or 10th digit. It is the significant digit here. So we rewrite that delta R as L cosine theta, remember? Divided by R squared. And that is the equation for the potential due to a dipole. When L is much, much less than R. When that number there is a lot smaller, that's this distance here, from here to here, between the 2 point charges. When that number L is a lot smaller than R, then you can use that as the approximation of the potential due to a dipole. Now, you start talking about the potential down in here, then you can no longer use that equation. Now you're going to have to do the math. That's what we did earlier, where we took the 2-point charges and we looked at the point right between them in the middle. You can't make the approximation there that delta R doesn't matter then. All in this region here, delta R matters a lot. You get all the way out there, it's not going to change anything. Now, dipole moment has units of Coulomb meters. And what is the dipole moment? It's Q times L, exactly. This right here is defined as the dipole moment. Yeah, I think so. Yep. It's exactly right. Coulomb meters. The name for those units is called a debye, D-E-B-Y-E. And except possibly on an exam, I'm not sure you're ever going to see it again. But the oh, actually, you know what? Let me make sure. Let me rephrase that. You might want to know this about the debye. It's actually a debye is by definition where'd it go? There it is. 3.33 times 10 to the minus 30 Coulomb meters is 1 debye. And they made that because on molecular scale it's handy, it's a more convenient, scale to work with. But in the table 17.2 on the bottom of 482, the left-hand column, you'll see they put the dipole moments directly in Coulomb meters. And I'm out of time, so I will see you tomorrow and we'll talk about capacitance in the lab.